Review. Okay. What we're going to start talking about today is functions, what denotes a function, how you can tell if something is a function. Can you find the domain? Can you find using function notation? And then eventually, probably start with it tomorrow, is we'll talk about what's called the function quotient. It's kind of like the first thing you guys are going to see that has anything to do with calculus. It's a pretty simple formula to use, but it just looks weird. And it stems from being able to use function notation. So just to go off the bat here, functions, remember, a function is nothing more than, this here. This is a whole lot of mumbo jumbo that I don't want you to write down. Because we know that a function is, for every x, there exists exactly one value of y. That's it. That's all this means. For every set from A to B in relation that assigns to each element x in set A exactly one element in set y in set B, then set A is the domain, blah, 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 blah. For every x, there exists only one y. That's it. Your input cannot give you two different outputs. Your input only gives you one output. That's it. One in, one out. That's a function. For every x, and what I mean by x, I'm talking like in some x value. There's only one corresponding y value. You guys remember a little something called that vertical line test from a long, long time ago? No, really?
I remember it, but I don't remember like how.
What you're doing here is, if you think about it in terms of just that vertical line test, if you remember nothing but vertical line tests for knowing something's a function, you're gonna be fine. Because no matter what you have, if you have sets of ordered pairs, if I'm looking at this, I'm trying to see if I look at this and I take any vertical line, if I take any vertical line and I go across a set of ordered pairs, as long as this vertical line only touches one of the ordered pairs at a time, see how this one would touch two of them? Is that better? See how it winds up touching two of them? That means that this value of x, the vertical, winds up giving you two separate values of y, which means it can't be a function. That's all that meant. And I know you guys all did a vertical line test at some point or another. So we know that if this wasn't here, if there's no repeated x value to at all, you're going to be fine, okay? And you know this from graphs. You knew that a parabola passes the vertical line test. But a parabola on its side, when we dealt with conics, a y-squared parabola, it didn't work. Because your values of x could have been in two places at once. So we knew that wasn't a function. Same thing with a circle. A circle wasn't a function because it doesn't pass that vertical line test. The x value winds up being in two separate ordered pairs in the graph. That's what that looks like. That's it. And I know you've done that. So they talk about in terms of domains and ranges. For every element in the domain, remember domains are your x values, there's exactly one element in the range. So what they went through here is some of the, I just want you guys to start to just kind of read how they explain things in more of a mathematical sense. Math language looks awful. It sounds awful. It's being able to read it so it makes more sense to you. Each element in A must be matched with an element in B. An element is a value. Something, some point matches to some other point. That's all that stuff means. Okay? If you're talking about elements within what's called sets, sometimes you will see it. Set notation with ordered pairs. That's all it is. You've all seen it before. You just didn't know that they were using really fancy language at some point. So the math that you have done in the past hasn't changed, okay? Some elements in B may not be matched with any element in A. They're just there. When we come across it, you'll see it, you'll recognize it. It just sounds weird. These are rules that you knew, okay? Another thing that you can tell that, excuse me, ways that you see functions written out. You had them as ordered pairs, tables, graphs, algebraically with equations. Any one of those could show some form of a function. You've done it. You knew that in a table, x and y, 1, 2, 3, 4, 5, 6. For every x value, is there exactly one y value? Is there anything that's been repeated? No. If you went through it again with ordered pairs, 2, 2, 2, 0, negative 2, and 1. Would that be a function? Why? The two values for the x, if you just think about it in terms of like a graph, if you're just plotting along 2, 2, and 2, 0, those two would be vertical of one another, and that value of x can't be in two places at once. That's what that meant. You've seen it, right? You've seen it. We'll talk about how to do this algebraically with two variables. It's really, really easy, and it's probably something you've done. So. Testing, this is where I'm getting at. If I'm looking at just these quick tables here, just like we did a second ago, that first one, let me blow that up some for you, sorry. Two, 11, 2, 10. What do you know right away? It's not a function. Can't be in two places at the same time. Can the y values be repeated? Yeah. Y values can be repeated because if you look at it, let's just say we had, we'll get rid of this. Let's say we had another point that was 1 and 10. All that means is that if you think about it graphically, here's 1 and 10, here's 2 and 10, 3 and 8, 4 and 5, 5 and 1. That vertical line is okay because it's not in two places at the same time. You can have repetitive y values, which just means a horizontal line. Horizontal lines are functions because it passes that test. Vertical lines are not because they don't pass. Does this vaguely sound familiar from one point in your lives? You guys did it in terms of, you did relations, tables, and ordered pairs in Algebra 1 a long time ago, okay? You did this. This is just fancier verbiage. The language just looks like crap. That's all. Doing these types of problems and saying whether or not something's a function is easy. You look at that graph. If you had your pencil out and you went across the graph, will your pencil touch 2 points at the same time?
Oh, I thought it was table and graph, sorry. What?
Then we're all good. What?
No. I said no because I was looking at the table and it was a graph.
I know, I was not going to what she said. Why is someone confused? She's laughing at what she said.
Yeah.
Why is everyone looking at me like this?
It's just awkward. It's just kind of fun. Algebraic. This is something that's a little bit different. When you want to test something algebraically for a function, what you need to do, and I wrote this out here, solve for y and make sure that's just a single value. Anytime you have to check an algebraic function to see if if you have to check something algebraically to see if it is a function, all you have to do is solve that equation they give you, get y by itself. As long as you don't have, or as long as it's a single value of y, you're good to go. And I'll show you what that means. If I take that first equation, x squared plus y equals 1, how do I get y by itself? Good, subtract x squared. just one value then? What do you mean no?
Yeah, it's
I don't know. Think about it. If you pick any value of x, are you just going to get one value of y? Yeah. Look what happens on the other one. The other one, you get y squared is x plus 1. But then you have to take the square root, right? What happens when you take the square root over an equal sign? That's where you get your plus minus. So here's your idea of y equals plus or minus the square root of plus u. Bless you.
thanks.
Welcome.
No, aren't those two both in graph, like they're not graph the same, like they're different graphs?
They're totally different graphs. This is a square root function with a plus minus on it. Remember when you guys did conics last year? I know in Algebra 2, no matter what class you guys were in, you did the parabola conic where it was either up like a cup, down like a frown, or opening left, or excuse me, right or left. This is the idea that you have this conic opening on its side. If you graph that, you wind up with two parts. It's symmetrical about something. It's not going to be in two places at the same time. This one would not be a function. Sir?
Can you graph plus or minus? Like when you type in plus or minus?
No, you'd have to do, on your calculator, you'd have to do one half and then the other half.
Oh, okay.
So if you typed it in with, square root of x plus 1, and then you do the negative square root of x plus 1, you'll get both halves of that curve. I don't think there's a plus minus button on this calculator. Yeah. You might as well have a remote start for your car too, right?
Actually, they do have plus or minus on lot.
They do?
Where? Go to that book, it's right next to the
What?
upkeep.
Oh,
Yes. I should probably start using this stuff a little more.
Yeah.
Where's the, what book are you looking at?
Oh, no, I'm just gonna.
Mine? Oh yeah, the book. There it is.
Oh, yeah, it says unsupported operator, so I think that you only put on the black ones.
Okay. I got you. I'm easily confused. So like I said, in something like this, you wind up having two possible values for y. When y winds up being a plus minus, that means you're getting two values. Okay? So that means that y can either be one or the other when you deal with that out. Right? So it means it's going to be two different places with that single value of x. That's what that looks like. Like I said, it's not anything crazy that you haven't done before. It just looks a little bit different in how it's worded to you. Okay? That's all. Which leads you to good old-fashioned function notation. Yeah, if it's a function, it's very similar to y.
Isn't it that we just put like points of x into the thing?
Why don't you come up and teach everybody? Yeah.
Or
No, I know, and I'm telling them, here, show them what you're telling them. You're right. Yeah, make up an example. You got it. Does everybody remember function notation? That's exactly all it is.
That was.
I know that all of you guys have seen function notation. Thanks, sir. Just give me a brief, that's all. Remember, function notation says f of x. That's how you would read it. F of x is. You'll see stuff where it'll say f of x is, well, like when he came up with there, x squared plus 1. What is f of 2? Well, that means you take 2 and you substitute in for x. Any x that you may have in that function. Sometimes they will do this. f of x is x minus 3. G of x is 2x plus 1. Now, what do you do when you see this?
Honestly, yeah, I look at that like.
Yeah, you did those. No, we did a little bit of them last year. Not that much. Go ahead, Cole. What do you do?
Would you substitute the g of x in first, and then whatever you get for that, substitute in for that?
That's exactly what you do. What happens here, and this is, I just kind of came up with a quick, scary version of something here. This looks like a giant mess. It's asking you what is f of g of 3. If you think about it in terms of order of operations, you've got a whole bunch of parentheses there. When you have a whole bunch of parentheses, you work on the innermost on your way out.
It was Jared too.
They're weird. You start on the innermost and just work your way out, just like you would earlier. So here on the innermost it says, what is g of 3? Well, g of 3 tells me to use the g equation and substitute in for 3. So you get f of whatever 2 times 3 plus 1 is. Very good. And then you just resubstitute back in. So you So the answer here, f of g of 3 is 4.
So that's the overall answer?
Yeah.
Oh, okay.
You work on the innermost order of operations, you just work your way out of it. And I know that you guys have seen that before. There hasn't been any craziness there. Another form of this is when you had piecewise functions. Do you remember those?
What?
Piecewise?
No, I don't think we
You may or may not have graphed those last year. It really depends. A piecewise, and I think that's what I had next here.
Whoa. Are we gonna get time to do our homework? 7.
Oh, we just did this. Oh, I do want to look at this real fast. I want to show you that example real quick. I have g of x is negative times x squared plus 4x plus 1. G of 2 is easy, just substitute in 2. G of t, what do you substitute in for x? T. If it said g of potato, what do you put in for x? That's all it is. Now it says g of x plus 2 now. What am I going to replace x with? X plus 2. Which means that you wind up with this. You get a negative out front, x plus 2 quantity squared. You see where I'm going with this now?
Oh, that's FOIL, isn't it?
Yes, sir. When you see something like that, we have to distribute and combine like terms. Okay? This is kind of how this quotient difference will start to work out when we look at it tomorrow. You'll have to remember to square stuff. Now, remember, junk squared is what? What is it? How do I? Junk times junk. So if you sat there and took x plus 2 quantity squared and you wrote x squared plus 4, what happens?
You killed the puppy.
Very good.
Wait, what?
You guys have never heard that? Mr. Sub would say that, and he'd be like, Mr. Murphy says this all the time, but I had like no idea who you were.
What?
Ladies and gentlemen, do not kill puppies. We like puppies.
I don't get it.
If you do,
You mess up
this
so
is
bad,
not
you
correct.
somewhere in the world.
This means x plus 2, x plus 2, which is x squared, 4x, and 4.
These puppies are adorable.
Exactly. Puppies are adorable. Except-
No, it's like because people
It has nothing to do with puppies.
No, I know.
It's like a
It's like you step on a crack, you break your mama's back. So if you accidentally stepped on the crack, you my mom's back crack.
You don't want to.
Remember, back to this because this is what, and you laugh. half of you are going to do this.
Nah.
Want to bet?
Yeah, 20. Then you just combine like terms, right?
Yes, sir. Then you distribute out and combine. So you've got your negative x squared minus 4x minus 4 plus 4x plus 9. 4x's drop. You wind up with negative x squared plus 5.
What do you do with that? Nothing?
Nothing. All you're doing is simplifying it out. You don't have to take out the negative. You don't have to do anything like that. There's nothing left there for you to do. Tomorrow, when we do something else, there will be something else to do. But this is the basic idea of when you have to square junk. Remember, it's junk times junk, guys. That's all I'm trying to get at. Right? That's all. We'll go into that piecewise thing. Piecewise. You may or may not have had a chance to talk about this last year. What piecewise functions are is that they are what we call domain restricted. Domain is which values, your x's or your y's? Your x's. And the reason why they're the x values is because domain comes first in the alphabet. So does x. It's convenient that way. Now, what happens here is that you could graph two separate equations on a single graph, and depending upon the domain, then your values would change. Oh, I'm sorry. Hey, sure, no problem. So what happens here is that we're not so much graphing these. We're just looking at function notation within these. So it says evaluate the function when x is either -1, 0, and 1. So they're asking you what is f of -1, what is f of 0, what is f of 1. -1, which of these two graphs do you, or which one of these two functions would you choose? Is it the bottom one or the top one? Is -1 bigger than or equal to 0, or is it smaller than 0? It's smaller than 0, so which one am I going to use? Top. That's what this is asking you guys to do. You won't have to worry, I don't believe you have to worry about graphing any of these things at all. What's up? Well, it depends on what the domain you're putting in for. These are domain restricted graphs. If you look at this graph, x squared plus 1, when it's less than 0, well, that's going to be going like this. When it's greater than 0, it's at x minus 1, and it's just a linear function from here. So this is an open dot, and this is going like that. If this is what that graph would look like. That's how you would graph that. Okay? Domain restrictive problems are very common if you think about really easy insurance. Car insurance from when you're 16 to you're 18 is one rate. When you're 18 to 21, it's another rate. When you're 21 to 25, it's another rate. It gets better because your age changes. Buying tickets to a movie, if it's a matinee, it's a cheaper price than it is later. Kids are sometimes cheaper than adults. Things like that. Those are domain restricted to how much something's going to cost. You see it very often. All these are telling you is, where does this value fit? Does it fit, -1 fit here, or does -1 fit here? -1 fits up top, so what's -1 squared plus 1? 2. 0, does it fit on the top one or the bottom one? The bottom one, bless you. So what is 0 minus 1? See how that works? It's just telling you which one are you going to choose. That's all a piecewise function is. You're picking pieces of the graph to substitute in. F of 1, which one does it go, top or bottom? Top. What's 1 minus 1?
Sorry.
Domain restricted. Okay? You're domain restricted. I don't think, we didn't graph these last year, did we?
No.
No, we skipped over on that.
Are we gonna graph this year?
What's that? No. Because graphing is easy, man. That's easy.
It's hard.
What are you talking about? X squared is a parabola, right? And if x is 0, what's your y-intercept? 1. I'm looking at the other side, I just made a curve.
What about the dots and the circles and all?
Ah! Remember when you had greater than and less than? Oops.
See, that's all.
You'd be surprised. If I show you this, you wanted to graph this. Number line, right? 3's in the middle, 0's here, 5's here. Circle it. Do you fill it in?
Yes.
No.
No. Because this is an open circle means it's not equal to. It's just greater than or less than. Which way are numbers bigger? Going to the right or the left? That's all it means. If this had a bar underneath it, then you would shade it in. That's all it meant. That's all it meant. Domain. This might be the last we'll get to today, so I don't think we'll have much time to get into anything else. The domain of the function is what are all your possible values of x? So if I have, I forgot to get the other equation here. If I have this, f of x is 2x plus 1. So I have 3 equations here. I'm going to start with the easy one. Is there any value of x here that it can't be? No. X can be any possible real number because you're never going to be dividing by 0. You're never taking the negative of a square root. You're trying to find all possible values here. So is there anything that it can't be? So this would be your all real numbers. You guys have seen that symbol, right?
No.
All right. That means all real numbers. You can write all real if you want. Okay? It's just an R with an extra bar in it. Okay? It's just an R with an extra bar. That means all real numbers. If I look at the second one here, f of x is the square root of x. Remember, can you take the square root of a negative? Can it equal 0? What's the square root of 0? Yeah. So here my domain will be the set of x's such that x, I don't think we'll do it this way.
But yeah, what is that?
I don't, so it's got to be x has to be greater than or equal to 0.
That's it? That's
Yeah. Your domain is this x has to be greater than or equal to 0.
Yeah, I don't know.
Okay? The last one's kind of messy. When you're looking at one that's kind of messy, especially when your variable's in the denominator, you're looking for the possible values that 4. Very good. You're looking at the zeros. What happens when you have a denominator, you set it equal to 0. And you just solve for x. Okay? Okay?
Why are you doing that?
Can you divide by
Add
0?
4.
No.
No.
No, that's why.
So you add 4.
So x can't be plus or minus 2. Okay?
That's all you do?
It cannot equal plus or minus 2 because if it is 2, what's 2 squared?
4.
What's 4 minus 4?
0.
Can you divide by 0?
No.
No. What's negative 2 squared? It's 4. What's 4 minus 4? 0. Can you divide by 0?
No.
This is where you guys worked with polynomials last year, and you wound up with, on your graphs, vertical asymptotes. Vertical asymptotes were where x was in the denominator when it was equal to 0. You also did that with tangent when you graphed trig functions. When you graphed trig functions, tangent had asymptotes at 90 and 270, at pi over 2 and 3 pi over 2, because you wound up dividing by 0 with those. And that's why it oscillated itself every pi rotation as opposed to 2 pi rotation. That's when we had those parameters. That's why their domains were a little bit different. Okay? So if you're looking at it, I think I had another one in here. If I go back to this here, let's look at B. I have 1 over x plus 5. What's going to be my domain there?
-5.
My domain, you're right, the 0 is at -5, so my domain will be everything but, yeah. So all I would say here, my domain is all x not equal to -5.
Is D all real numbers?
Think about it. Let's see here. If it's all real numbers,
No, it can't be 2. Well, no, any.
when you go to D, and I'm glad you saw that one real quick here. When you're looking at this one, we're trying to find where it's going to equal 0. Okay? Still can do it this way. Now, you don't want to take the square root of a negative. Do you agree?
Yeah. So you don't want.
So I don't want to get a square root of a negative. So if I move things around here and I think about it in terms of, is this going to be chunked? Is there a certain parameter this is only going to work in? What's that? Think about it logically. We know this, to make this 0, we know it's got to be 2 and -2, correct? So if I'm looking at it between 2 and -2, just logically, here's 0, here's 2, -2. Does 0 work? What's 0 squared? What's 4 minus 0? So it's still going to work. Does 2 work? What's 2 squared? What's 4 minus 4? What's the square root of 0? So it works. Okay. Does -2 work? What's -2 squared? What's 4 minus 4? What's the square root of 0? So they both work, right? What about 3? What's 3 squared? What's 4 minus 3? Oh, I'm sorry, 4, you're right. Thanks, Betty. What is 4 minus 9? Can I take the square root of -5?
No.
No.
Oh, I know what it's gonna look like.
What is it going to look
It's
like?
gonna look like -2, less than or greater than or equal to, and it's gonna be x right there.
What?
You're right.
What do I say?
What's
So
happening
like
here,
a number and
there's
then
a boundary between here and here that it only works. It can't be bigger than +2, and it can't be smaller than -2. But it can equal -2 and include +2. So you have a boundary of your domain will be between -2 and +2. I want you, when you see something like that, just think logically of what can or cannot work. You can find a 0 to that relatively easy. Set it equal to 0, and then you square both sides, add the x squared, and take the square root. You get plus minus 2. When it gets into the restriction then, well, does it work between them? Does it work on the outside? And I'm not doing anything more than looking at a number, let's see if it works. Okay? Work on day 1 of this stuff. We'll finish the quotient stuff tomorrow and kind of tie everything back together with any lingering questions, and we'll go from there. And we'll quiz out Friday. Hopefully,
no.
good times.